Okay, we're going to talk about mathematical modeling. We're not going to solve them though. We're only going to talk about some formulas and setting them up. We'll solve them at the end of chapter 2. So we'll revisit mathematical modeling again at the end of chapter 2. So we're going to start off with exponential growth. So exponential growth is defined to be the rate of change of population is proportional to the population. So what we want to do, since we've got population in here, we're going to set y to stand for population. So if y is population, then the rate of change of population, so the rate of change would be the derivative of the population, so dy, but it's with respect to time, so it's dy dt. So this is the rate of change of population, and it is proportional to the population. So the population is y, and proportional means it's almost equal. If the rate of change of the population goes up, the population goes up, and if one goes down, that goes down. But they're not exactly equal. They're just, you have to offset it by k. That's what proportional means. Okay, and in here, we're going to have k is greater than 0. Okay, and so basically we just have exponential decay. It's exactly the same thing, but that's when our k is negative. That's when it's decreasing. The rate of decay is decreasing. So exponential. So like I mentioned, exponential decay, when the k is negative, it gets smaller, and so it's decaying. We'll learn how to solve these two equations later in the next chapter, but for now, I could go ahead and tell you that their solution is going to look like this. So our second formula that we're going to look at is Newton's law. And Newton's law, basically, you can read what it says. It's the rate of change of the temperature with respect to time is proportional to, so that's proportional to the change in temperature and the outside air. So that's TA is the outside temperature. So if the temperature is less than the outside temperature, then we have a warming that's going to happen. And so later on, we'll have a fun example on temperature. You can use this formula to find how long a body's been dead, for example. So here is a formula for falling bodies, and you can see we're just using the common formula F equals mass times acceleration. So A is acceleration, but we also know acceleration is the second derivative, so we can replace A with the second derivative of the distance in terms of time. And that's all. This is also equal to minus mg. So basically our acceleration is minus g, negative because it's going downward. So here we have a mixture problem, and our mixture problem is going to have 1,000-gallon tank. It's going to be 1,000 gallons of water in the tank that has a 4-gallon per minute inflow and outflow. And it also is mixing 3 pounds per gallon of salt into the tank. So what we want to do is we want to find the differential equation for the amount of salt in the tank at time t. What I think will be helpful is to set y equal to the amount of salt at time t, since that's what we're looking for. It says to find the amount of salt in the tank at time t, so that's exactly what we set y equal to, because that's what we want to find. If we want to draw a picture of a tank, we can do that. We have an inflow We have an inflow and an outflow. And we have an outflow. So inflow, we can put in our formulas. 4 gallon per minute. We also have an inflow of 3 pounds per gallon of the salt going in, and out is also 4, the water is going out at 3 gallons per minute, and there's 1,000 gallons in there. Okay, so we know we want to solve for, right, we're not going to solve for y, we want to set up an equation and then solve for y, which we won't do today. We won't solve, we'll just set up the equation today. Since this is rates going in, going out, well, we know we're gonna also have to work with the rate of y in terms of t, right? So this is the rate of the amount of salt in terms of time t. The units here, I like to keep my eye on the units. Y is the amount of salt is in pounds. So we have pounds per time, and it looks like it's per minute. And since we have in and out, so the rate, okay, since we have in and out, the rate of y in terms of t can simply put in words, it's equal to the rate in minus the rate out. So we need to figure out those rates. So we have a lot of rates going in. We have 4 gallons per minute and 3 pounds per gallon. And what we want is pounds per minute. If you can just kind of figure out the rates, we need to have pounds per minute minus pounds per minute. So the rate in, we have 2 rates over here. And remember, we want to make sure that it's in pounds per minute. So if we take 3 pounds, the salt, 3 pounds per gallon, and times it by 4 gallons per minute, it looks like we will have 12, the gallons are going to cancel, and we'll have pounds per minute. And then let's figure out the rate out. Well, the rate out, we do have our 4 gallons per minute. So we will also need our pounds, pounds per gallon. But what do we need our numbers to go in front of there. So we do need our pounds per gallon. So how many pounds of salt do we have? Well, we don't know, right? Y is the pounds of salt. So it looks like our Y will go on top. And how many gallons do we have mixed with it coming out? Well, it's getting mixed with 1,000 gallons. So we can see here the gallons cancel, and I get the 4 cancels into the 1,000, y over 250 pounds per minute, which is my dy dt. And clean it up. You don't have to write it with the units. And here is my dE, that when I solve for y, I've solved for y is the amount of salt at time t. Okay? And that's the end of this, real short section, so probably want to do 2 sections today.